All right, ladies and gentlemen, welcome back to your favorite class. Yes. Okay, a couple of announcements. I got them popped up on the screen there. Homework 2 has been posted. It's going to be on micromechanical models, which is what we're covering. We sort of started in on a little bit yesterday. On Thursday, but we're going to dive in a little bit more deeply today and probably finish up the topic tomorrow. So sort of the micromechanical notes, I think, will be for long fibers, continuous fibers will be done. Then we'll dive in on short fibers and particulate micromechanical models, probably Tuesday and Thursday. And your first micromechanical model homework, which will be on continuous fibers, will be due next Tuesday. That's been posted to Blackboard. You can take a look at that. You should be able to get, somewhere with it after today's lecture. And if not after today's lecture, definitely after tomorrow's lecture. Okay? So that's that. Your manufacturing assignment has also been posted for those of you that weren't here in lecture last time, just to make that clear. That's on Blackboard. That's due, I don't know, a couple weeks from now. So, yeah, that document's on Blackboard. Okay, so let us get back to what we were doing previously. Bam. Let me get rid of this, actually. Get this guy back. All right, so let's kind of remind ourselves where we left off last time, and we were introducing micromechanical models. And micromechanical models are sort of like the smallest model that you could possibly think of for how fibers and matrix might interact to give you material properties of a composite. All right, so let's recap here for our micromechanical models. So remember, this is kind of like the smallest possible model that you could think of, a singular fiber surrounded by matrix. So kind of the model that you should have in your head looks something like this. Where you've got sort of like a single fiber here, surrounded by matrix. All right, and we're going to assume that whatever properties we distinguish from this one tiny little model, we could replicate infinitely as sort of like a repeat unit to represent what would be like a composite as a whole. So if we could figure out what the properties of this little guy is, then we could extend that to our whole composite and say, here's the modulus of our composite, here's the modulus in this direction, here's the shear modulus, here's Poisson's ratio, all those sorts of good things. All right, so this and assume hold for full composite. Okay. That's the general idea. We started in by first introducing the idea of volume fraction, and it's a pretty straightforward explanation of volume fraction and what it is. It's the fractional component of each one of the things that make up your whole. So our volume fraction, we kind of discussed at the very end of last lecture. We said that, let's say, a fiber volume fraction. Oof, writing is hard. Maybe something like capital V sub F is the total volume of the fibers divided by the total volume of the composite. I'm not going to rewrite the definitions. I sort of explained what these are last time. So volume fraction ranging from 0 to 1 or 0% to 100%, however you want to think of it. You could similarly have matrix volume fraction, which is going to be something like Vm is the volume of the matrix divided by the total volume of the composite. And we said that if we assumed that the composite had no voids, is only made up of fiber and matrix, that we have some additional relationships that we can sort of leverage. And that is no voids, meaning no empty space, that the total volume fraction of the fibers is going to be 1 minus the volume fraction of the matrix. Or you want to sort of think of it this way, the matrix volume fraction and the fiber volume fraction together have to be 100%, right? Either way that you want to think about it, it's perfectly fine. Now, we looked at some simplifications that we're going to use for our micromechanical model, and that is specifically if you're looking at a cross-section that is just containing sort of the cross-section of the individual fibers, and you have a unidirectional composite, meaning your composite only contains fibers that are in one direction. So we'll say for unidirectional composites, with 2D cross-section, the areal fraction is a proxy for volume fraction. So what I mean by that is, if we assume that the cross-section that we're looking at, which might contain a bunch of fibers and might contain a bunch of matrix, we counted all the area of the cross-section that contains fibers and assumed that that is extending into the plane, that would be a proxy for volume fraction. So you could say something like the volume fraction of a piece, which is the volume of the fibers divided by the volume of the composite, is going to be equal to whatever length of the fiber is running into the page for this particular cross-section, multiplied by the total areas of fibers that you see in the cross-section in front of you, divided by the length of the composite into the page, multiplied by the total area of the composite. So this is like two volumes. Length times an area is going to give you a volume. Or since we assume that we have the same thickness of both components into the page, you're just going to have something like the area of the fibers in the cross-section divided by the area of the composite. So this is sort of a proxy that we're going to use with our micromechanical model. And maybe what you might want to think of in your head is some cross-section that looks like this. Where let's say like all of these, I don't want to use black. Where you see like all of the area that's occupied by these fibers. Well, if we assume that those fibers are running into and out of the page with the same thickness as like the matrix, which is kind of all this black material that you see here, that we could estimate the total volume fraction of this composite by just calculating what the area of the fibers is in this cross-section and looking at the total cross-section itself. So maybe here we could estimate a volume fraction of, I don't know, 65%? Does that seem appropriate? That's 65% full of fibers? I think that might be a good guess. All right. Now, there are some limits on volume fraction for real composites. And this mostly comes down to like the packing that you could have for fibers in a cross-section. So you've probably familiarized yourself with like hexagonal close packing or like, you know, cubic packing from your material science classes. Like the same sort of principles from those material science classes apply here and kind of give us a realistic upper limit on what we might have for volume fractions of composites, specifically unidirectional composites. So realistic upper limits on volume fraction are governed by packing of the fibers. All right, there's two kind of packing models that we might consider. Square packing and hexagonal packing. Those are probably going to be the two that you started talking about in your material science classes, and so you've probably seen this before. And if you assume sort of like a perfectly patterned arrangement of like fibers inside of a cross-section, then you might have a picture that looks like this. if you assume a perfect pattern of circular fibers in a cross-section, and think about square packing first. Well, for square packing, you're going to have something that looks like this. So square packing the fibers, they're all kind of perfectly patterned, perfectly spaced, sort of this square arrangement. Okay. Now we could look at the square arrangement and pick out for ourselves a unit cell. Hopefully we're familiar with the concept of a unit cell. Might have a question here in the chat. Just a second. Question. My mic is off. No, my mic's not. My mic is going. All right. Square packing. So you might pick out for yourself a unit cell, and that unit cell might look something like this. And the idea here is that you want to pick out something that can be a repeat unit used over and over and over to represent an infinite structure, right? So here's our unit cell. Right? And if you consider some variables like, let's say here we have, I don't know, diameter of a fiber, give it a variable d. And let's say that there's spacing between each one of these particular pieces. Let's draw it somewhere else. Say there's a spacing here of little a. Well, there's a maximum amount of fibers that you can fill into that space by, let's say, maximizing D and minimizing A or something along those lines. All right. So in a square packing arrangement, the maximum volume fraction that you can get, and you can sort of prove this mathematically, is that you should have a maximum upper limit here of about 78.5%. Right. You may also consider like a hexagonal packing arrangement, which is like the absolute maximum upper limit. This is like the best you could do. And it would look something like this. Where you have these guys sort of like offset with each other in this sort of like triangular pattern. It's like the best way to arrange cookies on a cookie sheet if you're going to bake. Optimal packing. All right. I have a question from the audience. Yes, sir. The question is, if you have a very high volume fraction of fibers, is there some point where the fibers are somehow weakening the structure? In theory, no. In practice, yes. And we're going to discuss the differences as the class progresses, okay? I'd say hold your question for another week and a half and answer it and ask it again if I haven't quite answered it. All right, so I got my cookies on the cookie sheet. The best arrangement. Now I want some cookies. Dang. And we could consider a unit cell that might look something like this. All right. Here we have a distance between pieces that is sort of the minimal distance between the two, which we might call a little h. And again, we have the same like fiber diameter, assuming they all have the same diameter, that is d. There are models that exist that sort of show that there's a maximum volume fraction of packing. It used to be a homework problem that I give to derive the maximum value, but people went crazy with that, so I decided against it. You're welcome. The maximum packing for hexagonal packing is 90.7%. 90.7, the temperature of my heart. Cold-hearted. That was the joke. Unless it's centigrade, and then I'm like very warm-hearted. Maybe I'm just Kevin-hearted. Okay. So this is like the absolute upper limit maximum. And remember that like the strength and the stiffness of our composites is going to be governed by the amount of fibers that we can incorporate. So generally, like the more fibers that we can get in there, the better. And so you want to approach the highest value you can when you manufacture composites. I will say in real application, the max I've ever seen is like 70%. And that's like really doing as much as possible to get everything all in there nicely. Okay? So I'll say here in practice, volume fractions of greater than or equal to 65% are incredibly good. All right? Very good. Think aerospace grade, you know, pieces that go on the Boeing 787. All right, unidirectional fabric stacked on top of each other, giving you VF 65% are great. All right, very, very good.
I have a quick question.
I got one in the chat and one in the classroom. Let's go with the guy in the chat first. Go ahead, online.
Okay. So as far as the fibers go, those are generally like the more dense materials that give strength to the material, right?
So the
So,
question is, go ahead.
I given that fact, would packing a bunch of fibers in essentially make it lose its lightweight but strong, I guess like specific strength? Would it lose specific strength
Sure.
if you pack in too many fibers?
Right. So the question is, because the reinforcement is generally more dense than the matrix, do you lose the benefit by incorporating more fiber material? And the answer is no. That's because the stiffness of the fibrous phase, the reinforcement phase, has a greater increase in strength than the increase in density associated with that particular material. That makes sense? So even though my fiber might be twice as dense, it might be 10 times as stiff. Okay? So yes, you are making it generally heavier, but you're also making it significantly stronger. Okay? So it's a nonlinear relationship there. Next question from the audience. What percentage is prepreg? When you get prepreg, it's usually a little high on the matrix, just because some of the like epoxy will come out during the manufacturing process. But say if the prepreg and its unidirectional prepreg is handled and manufactured correctly, you're going to get it in the 65% range. All right? That's how you get the 65%. It's generally gotten through prepreg autoclaving techniques. Okay? Woven composites and others are lower. So remember, when we talk about woven composites, I mean like the plain weave fabric, the satin fabrics that I talked about last time when I talked about manufacturing. So most are still good at 50+%, and most woven composites in this range. 50% is still quite good. You'll get tremendous benefits over aluminum and steel still at 50% volume fraction, right? It's once you get to like 25-30% that you're like maybe dancing on the border of having benefits over traditional like steels and aluminums, right? You're dancing on it. All right, so there you go for volume fraction. Now, enough ado about this volume fraction nonsense. Let's actually get into the mechanics. Volume fraction, I think, pretty simplistic and easy idea to understand. The more fibers you get in there, the stiffer it's going to be. Let's put some math to that with some micromechanical models. Enough ado. All right. First thing we're going to talk about is the mechanics of materials approach. As I mentioned, we're going to look at two approaches, the mechanics of materials approach and the help and psi approach. All right. So the first approach here is mechanics of materials model. And there are generally two submodels associated with the mechanics of materials model. The first is the parallel response, or the rule of mixtures response. B and E. Gosh, handwriting not so good. The parallel response, sometimes called the rule of mixtures. All right. So what is the basis of this model? All right, well, this model here is basically we're going to assume all these fibers are in kind of like a parallel arrangement, and we're going to load that structure in a parallel manner to the fiber. So kind of the picture that you should have in your head here is that you've got a composite that looks like this. And you've got a number of fibers that are kind of like in this structure that are kind of running in this direction here. And remember,
Sorry, I didn't quite catch that.
Oh,
could you please repeat it?
Quiet down, Siri. And remember that all the fibers are sort of running along this general orientation. So let's say they're carbon fibers, so they're all black.
Sorry about that.
Siri, quiet. Okay. Here's our general model. We've got a bunch of fibers here, and this is like a unidirectional composite. And we'll remember that with our coordinate system, our fibers always run in the one direction. All right, so here, this might be like the 1, 2, 3 coordinate system. So what we're going to do here is we're going to make assumptions about the stress and the strain response of the fibers in the matrix and sort of get some relationships out of those assumptions. So here, the parallel response, we're going to assume the fibers in the matrix have the same strain in the one direction. All right. So let's do an example, and we'll motivate this example by trying to determine what the modulus is of this composite using information about the moduli of the fiber in the matrix. Right? So here we'll sort of motivate this with an example. Of composite in one direction. We label this generally as E1, right? Makes sense. Modulus in the one direction. And this is going to be from moduli of matrix and fibers, which we'll label as EM and EF. Makes sense? So some assumptions that we need to make to move forward with our model. Okay, first, we already talked about this, is that the fibers in the matrix have the same strain in the one direction. We call this an Isostrain Assumption, meaning that the strain in the one direction is the same as the strain in the fibers, which is the same as the strain in the matrix. This is mathematically how we write this. If we want to get specific about this, we could put subscripts 1 on here for the fiber in the matrix, just to make sure that we know that we're talking about the strain of the fiber in the one direction, the strain of the matrix in the one direction. I think that's kind of intuitive, but put that there just for absolute clarity. The second assumption that we need to make is that there is a perfect bond that exists between the fiber and the matrix. So we're assuming here that the interface is perfect. Okay? Perfect bond at interface. That means that the load is perfectly shared between the fiber and the matrix. Okay? And also we're assuming linear elastic response. that just more or less means that the stress tracks linearly with the strain for both the fiber and the matrix. So like Hooke's law, right, is your linear elastic response. All right. Stress, strain have a linear relationship. All right, these things are important for our model, and I'll sort of point out why that is as we go. All right, so our model, on its most basic and simplistic view, is that we're going to look at what's happening with one particular fiber in the surrounding matrix. So what you really want to think of is not all those fibers in one composite, but a model composite that just has like one single fiber in it, like this. So here's your singular fiber. Just like me, I'm single, ready to mingle. No, I'm just kidding. I have a fiance now. All right, so here's our one singular fiber in the surrounding sort of matrix material. All right. And the idea here is that we're going to put a force on this particular piece in the one direction. All right. So here we are. Maybe we'll do it in blue. And I'll call that F1. F1. All right. So apply a force. And force distributed. Two fibers. Matrix. And we're going to assume that that force is distributed to the fibers in the matrix by writing this mathematically as like this force that we applied has some component which is in the fibers in the one direction plus some component that's in the matrix also in the one direction. All right, write that or not. We can convert this to stress in the one-dimensional model. And so our force in the one direction could be the stress multiplied by the area. So that might be something like the stress in the one direction multiplied by the area generally of the composite cross-section, let's call it AC, is equal to the stress of the fibers in the one direction in the area of the fibers plus the stress of the matrix in the one direction, the area of the matrix. And this specifically is the area of the fibers in, let's say, the 2-3 plane. All right, so hopefully we're clear on that. These areas we're referring to here. This is in the 2-3 plane. All right. So like the picture that we saw before where we sliced it and saw those fibers, etc. You get the idea. All right. So let's now divide by the area of the composite. And we can use that volume fraction relationship that we had before. And so we'll just say convert to volume fraction. So on the left-hand side, I sort of divide by the area of my composite. And I'll simply have the stress in the one direction on this piece is the stress on the fiber in the one direction multiplied by the area of the fiber divided by the area of the composite, which we know to be the volume fraction of the fibers. This is back from slide 3 on the deck, or we talked about it in our recap today, plus the stress that the matrix hold, sort of in this one direction if you want to keep the one going, multiplied by the volume fraction of the matrix. Sort of seems obvious that the stress in the piece is the combination of the stress in the fibers multiplied by the amount of fibers that you have in the cross-section plus the stress in the matrix multiplied by the amount of matrix. All right. Now we'll keep going. and we'll assume 1D Hooke's law, which, as you all know, that means they don't know, is sigma equals E times strain. Okay, you guys probably didn't know that. I'll just fool you. This is that linear elastic relationship or assumption that we had to make. Okay? If we do that, we're going to have the modulus in the one direction times the strain in the one direction is the modulus of the fiber in the one direction times the strain of the fiber in the one direction multiplied by the volume fraction of the fibers plus the modulus of the matrix in the one direction times the strain of the matrix in the one direction multiplied by the volume fraction of the matrix. Okay. Our last assumption that we have to bring in is our isostrain assumption. And that more or less just allows us to cancel the strain out of this equation. We're saying that as we're pulling the fiber and matrix together, because we have this perfect bond between the two of them, they're going to strain at the same rate as we pull on them. Okay? They're going to strain all together the same amount. So with that idea here, we have E1 is equal to the modulus of the fibers in the one direction times the volume fraction of fibers plus modulus of the matrix in the one direction times the volume fraction of the matrix. This general equation here, this form of this equation, here is known as the rule of mixtures, or what we call the parallel model. And if we just look at this equation and think about it, it is intuitive. All right, so here, this is the modulus of the composite. In the one direction is basically a linear combination of the modulus of the fibers and the volume fraction of the fibers plus the modulus of the matrix multiplied by the volume fraction of the matrix. Okay? So I'll say normalized stiffnesses of constituents. All right? If we put more fibers in, that VF value will increase, and generally the stiffness of the composite in the one direction will increase. If we put more matrix in, that will reduce the volume fraction of the fibers, give you more matrix, and generally reduce the stiffness. Okay? I have a question? No question. All right, just someone trying to get in. All right, so this is specifically for the modulus in the one direction. All right. So here we are. The last thing I'll say is typically matrix materials are isotropic. So the general idea is that the modulus of the matrix in the one direction is the same as the modulus of the matrix in the two direction, is the same as the modulus of the matrix in the three direction. So we generally just drop the directionality associated with the stiffness of the matrix phase, and we will just write like capital E sub m. We'll sort of make that assumption in this class going forward. When we talk about like epoxy matrix, yeah, that's isotropic. You know, when we talk about thermoplastics, when we talk about even a metal matrix phase, whatever, it's generally going to be isotropic behavior, okay? However, many fibers are not. Okay? carbon fiber. I'll write it out. Sorry, not here. Ergo carbon fiber and Kevlar. Okay, so must retain the directionality like EF1, for instance. Got to retain that subscript modulus of the fiber in like the one direction. It's because like the modulus of a carbon fiber in the one direction is not the same as the modulus of a carbon fiber in the two direction. All right. So more commonly, you'll see the equation for modulus in the one direction will be VF times EF1 plus VM times EM with no directionality associated with the matrix stiffness. The resulting Poisson's ratio, you could go through the similar sort of calculation for the Poisson's ratio and come up with a very similar looking equation. In 1-2 direction. Specifically for the 1-2 direction. Used to be another thing I would assign for homework, but I'm not doing it this time around. Should be thankful for that. Instead, you have to do limits as something goes to infinity, which is much more fun. All right, so here, volume fraction of fibers multiplied by Poisson's ratio. It's kind of hard to distinguish Poisson's ratio nu from volume fraction V, but I'll do my best. The fibers, specifically the 1-2 Poisson's ratio. Remember, Poisson's ratio is the ratio of strain in one direction versus strain inverse in the other direction, the negative strain in the other direction. And here we drop the subscript for the Poisson's ratio of the matrix and end up with something that looks like this. Okay, so here we are, able to calculate the modulus of the composite and the Poisson's ratio of the composite given constituent properties of the fiber in the matrix. So you might see as the following. The property of the composite is the volume friction of the fibers times the property of the fibers in the one direction plus the volume fraction of the matrix times the property of the matrix. This is the most general form of what is known as the rule of mixtures, where this P here stands for property. So this is the general rule of mixtures. Or parallel model. The rule of mixtures is really only good for calculating E1 and nu1, 2. Other calculations, much more suspicious. Like, you don't want to start calculating the modulus in the 2 or 3 direction using this model. You don't want to start calculating Poisson's ratio 2-3 using this model. You don't want to calculate shear modulus with this model. Those are all not the best. That's because there's another model. So let's talk about that other model. That'll close out our parallel model discussion. And now, the next model. The mechanics of materials model again. But here now we're looking at the series model. So just like in your circuits class, you have like parallel models for resistors and series models for resistors. Very similar idea. Okay. So here we're going to make a lot of similar assumptions, except now we're going to put our load in the 2 direction instead of the 1 direction. All right. So the series model assumes fiber and matrix have same stress. All right. So previously our model said that the components had the same strain. Now we're going to assume that our piece has the same stress. And the idea here is we're going to load it in 2 direction and sort of see this isostress in action. So load in 2 direction. And derive. So let's look at an example. With, let's say, the modulus in the 2 direction. All right. So the model you should kind of have in your head is we've sort of taken our composite now and like flipped it on its edge. We're still going to have our one single fiber inside of the matrix. Fiber in the matrix. And now we're going to load not in the 1 direction, but in the 2 direction. But remember, we still have something that looks like this, right? 1 direction always in the direction of the fiber. And now we're going to load in the 2 direction. So here we are, to F2. And we can see now how maybe the isostress model is a little bit more appropriate, right? You've got this force that's sort of like got to act over a stressed area that might be like this area here. And in the fiber, that same stress is acting over what would be like this area here into the page, right? So you're going to have similar stresses if you have similar geometries of like these fibers in the matrix, right? So let us move with this idea in mind. We're still going to make very similar assumptions, but the biggest difference is we're going to have isostress. Okay, so what I mean by that is that the stress in the 2 direction of the composite is equal to the stress in the 2 direction of the fibers, which is equal to the stress in the 2 direction of the matrix. We still have our other 2 assumptions, and that generally is perfect bond. Bond. Perfect bond. And linear elastic. You guys ever watch those old James Bond movies? They're still actually like really good. Like, man, go watch View to a Kill until you're not entertained. Okay? That movie is fantastic. Right? He's like throwing people out of blimps. He's like, you know, saving a mine from destruction and dynamite, and all the while, you know, wooing all the ladies. Right? It's amazing. Go James Bond. All right. So what we're gonna do is let's consider what's going on with the little model, and we're gonna start with the deflection or displacement in 2 direction. Okay, which will be a combination of what we get displacement-wise from the matrix and what we get displacement-wise from the fiber. Since we're assuming they each have the same stress and they're going to have different moduli, they're not going to have the same total displacement in our model. So the idea here is that the deflection in the 2 direction is going to be a combination of the deflection of the fiber in the 2 direction plus the deflection of the matrix in the 2 direction. Each one of those is a lowercase delta, meant to stand in for deflection. Some people like uppercase delta, but I like lowercase. Okay. So strain in 1D, remember, is something like the strain is the deflection over the total length. And we're going to say that in this model that we have, original length of fiber or matrix is going to be sort of the thickness here, T of the fiber and T of the matrix. So what do I mean by that? Well, if we go back up to this model here, here's the thickness of the fiber. And then the total thickness of the matrix is what we consider here. So it would be sort of this guy be half of it, and this guy would be the other half. So the total thickness of the matrix would just be Tm. With that in mind, we could start making replacements here. It would be something like the total strain in the two direction of the composite multiplied by the total thickness of the composite, which we'll just say is Tc, is equal to the strain of the fibers in the two direction times the thickness of the fiber plus strain in the matrix in the two direction multiplied by the thickness of the matrix. Where here we've kind of used like L is equal to T. It's the original undeformed length of each one of these components. So here divide ITC and use volume fraction relations. You're going to end up with the strain in the two direction is the strain of the fiber times the volume fraction of the fiber plus strain in the matrix times volume fraction of the matrix, all these in sort of the two direction. All right, now Hooke's law. Stress in the two direction, modulus of the two direction. Here the strain is the stress divided by the modulus, equal to the volume fraction times what would be the stress in the fiber in the two direction divided by the modulus of the fiber in the two direction plus the volume fraction of the matrix times stress of the matrix in the two direction divided by modulus of the matrix. I'm going to drop the 2. We know it's the same in all directions. And now our last thing is isostress, meaning all these stress components are equal, and you end up with 1 over E2 is VF over EF2 plus VM over EM. And here is your inverse rule of mixtures. Also known as the series model. Okay, baby! This is used for E2 and also G12. So if you're looking at the shear modulus in the 1-2 direction of your composite, it's the volume fraction divided by the volume fraction of the fiber in the 1-2 direction plus volume fraction of the matrix divided by shear modulus 1-2 of the matrix, or you might just see it as shear modulus of the matrix, since we know that it's isotropic generally. All right, so that is your inverse rule of mixtures. Okay, thanks for coming. 1 minute over. Apologies for that. Have a great day and whatnot, etc.